the thing about imaginary solutions is that they always come in pairs. So if you have a quadratic, like something to the effect of z squared minus 2z plus 5, if it doesn't have real solutions, then both of the solutions are imaginary. Now a cubic, like we have down here, I'm going to assume, and I'm going to be right, that there's one real solution, possibly 3 real solutions, but not 2 real solutions and 1 imaginary, because the imaginaries always come in pairs. So let's get our factoring hats on. Your favorite 4-lettered, six-lettered F word, factor. Let's do it. How would I factor A? What in the world? What if I did this? What if I said u equaled x to the second? Does it look easier now? Yeah, a lot easier, right? So if I could factor that by going, I know that has to be a 3u and a u. What numbers would multiply together to give me 4? Well, 2 and 2 or 4 and 1. But I've got this coefficient out here that's going to be doing some funky stuff with that. What would that be? Let's see. 2 and 2, is it? Okay, it was that easy, huh? Okay, so now I go back and I sub in what I had, which would be x squared and x squared. And if I were to FOIL that, I should get what I had above. Okay, so if your powers are maybe something that isn't so easy to work with, you can always do a sub on it. Okay, so now let's talk solutions. So the zero product property, the ZPP, tells us that if we want to know where that equals 0, then we set both of them equal to 0. Okay, and then we solve. Because if 1 equals 0, then they both will, because it's a product. Okay, so I'm going to subtract 2 and divide by 3, so x squared equals negative 2/3. So then what does x equal? Well, the square root of negative 2/3. Well, we can't take the square root of a negative number, so how would we write that? What would we pull out of there to bring that negative out? I. So those would be our 2 solutions there, right? On the other factor, let's find the roots of that. So x squared equals negative 2. So x equals plus or minus the square root of negative 2, which means that x also equals plus or minus I root 2. Now I want to make something pretty clear here, because this is common misconception amongst well, some. But here I have factors. Okay, highlighted in yellow, I have factors. And down here, does anybody know what these are called? Roots. What's another synonym for it, or whatever they call that? Cinnamon, whatever. I don't know. I do them the numbers. Roots. What else? Zeros. What else? Solutions. Okay, so these are roots. They could also be called zeros. They could also be called solutions. And yes, I will be grading your papers, which means I'll probably ask you to use a bunch of cinnamons. Okay, cool. So that's got 4 roots, all of which are imaginary. So does that function ever cross the x-axis? No. No real solution, so it never crosses the x-axis. Okay. All right, let me go into another method of factoring that may or may not be in your memory, but if we don't have at least one of the solutions to said function up here, we can't do like synthetic division or long division to find the other roots. Therefore, the only other way to do this is to do factor by grouping. Do you remember factor by grouping? Okay. Here's factor by grouping. I'm going to group the first 2 terms, and then I'm going to group the last 2 terms. And then I'm going to factor out something from those terms, if possible, right, to make them the same. So what can I take out of the first? Z squared. Oh, and look at, conveniently, that becomes 2z minus 1. And what can I factor out of the second one? Well, I wouldn't factor anything out of that. I would consider a 1 on the outside there. Now, what can I factor out of both of those expressions? 2z minus 1. So I can factor out a 2z minus 1. That leaves me with what? Z squared plus 1. Okay, so before I said you're going to have potentially 1 or 3 real solutions. How many do we have? Because these are the factors. Let's talk zeros, solutions, and roots. What would make this equal 0? If z equals 1/2, right? So that's our real solution. Okay, what would make this equal 0? Nothing real. Yeah, plus or minus I. Right? If I took the square root of -1, I'd get plus or minus I. Okay, and there are our solutions. So we've got those 3 solutions. How many times does this function cross the x-axis? Once. The imaginary solutions are not x-intercepts. Okay, only the real solutions. These solutions. Well, these solutions, if, let's say you don't know the polynomial, right? But you do know the solutions. Then what we can do is we can write out factors, right? So 2z minus 1, we could write a factor out of that. And we could write 2 factors out of this. If I were to solve this and set this equal to 0, what would I get? I'd get z plus or minus I equals 0. So technically these are my factors. I'd have z plus I and I'd have z minus I. And now I could FOIL this and then distribute that, and I could come up with my polynomial. So if you have all of your roots, you could find your polynomial by doing a bunch of FOILing. Correct.
Why did we do it the way we just did?
To show you one way that it's used. Now, is it applied in kind of like a calculus sense? No, but it's a skill that you need to have. Okay. All right. You good at that? Should we move on? Okay. In this case, this is a toughie to factor, but the conjugate root theorem is going to assist us. Complex roots, which are imaginary solutions that have an I involved, always occur in conjugate pairs. So like the last one was just plus I and minus I. This one, we've got a factor of z minus 1 minus 2I. Let's find out what that root would be. If I set this equal to 0 and I get z all alone on one side, what would I get? Z equals 1 plus 2I, right? What would the conjugate of this thing be? Correct. So the conjugate of that would be 1 minus 2I, which would tell me if I want this equal to 0, I can now find that as a factor. I would subtract 1 and add 2I. So my other factor would be this. So I now know this. This is a factor of our cubic polynomial over here, and so is this up here. So we could go about finding the third factor, right? Which it has to be real because you always have imaginaries in pairs. So what the heck? Basically what I want to do is this. And it's going to be a lot easier than maybe you're anticipating. But I'll show you how. I don't want to FOIL that in that way. So what I'm going to do is a special type of FOILing, which scares people. I'm I'm going to write it like this. And z minus 1 plus 2I. And then I'm just going to go about my business. Okay, I'm going to multiply that out. Well, what would I get if I multiply that out? Z squared minus z plus 2iz. What do I get here? Minus z plus 1 minus 2i. One more time. That's minus 2iz plus 2i minus 4i squared. Now let's analyze this and clean it up. I see a 2iz. Am I recording? Yes, I am. Good. I see a plus 2iz. I see a minus 2iz piece. See you later. What else will cancel? Yep, minus 2i and plus 2i. Those go away. And that will always happen if they're conjugates. So let's clean this up a bit. That'd be z squared. I got a minus z and another minus z here. That's minus 2z. And then I got this 1 and this. So plus 5. Sick. Okay, so I got this. And I know there's one more factor, and it gives me the polynomial above. Now, watch the cool stuff I'm about to do. How come I don't care about the terms in the middle? Nope. Because what do I know has to go there? A z, which z times z squared will give me z cubed. And how do I know it's going to go here? Oh, is it 2z? Okay, good. All right, then I know there has to be a 2 there. Thank you. 5 times what gives me 5? 1. Done. Finished, right? Do I want the roots or did I just want it in factored form? Toffee to factor. Okay, that's factored. Now, technically speaking, I should write this. This would be in factored form. Equals all the stuff that we had above. And we've got our factored form. And we've got our roots. Right? If I wanted to know what the root of this was, again, let's cover this. I don't think I can be deliberate enough with this because it's necessary. I'd set that equal to 0. Same thing here. Set that equal to 0. Same thing here. Set that equal to 0. So I get z equals negative 1/2. I get z equals what? 1 minus 2i, good. And then my last one, I should get z equals 1 plus 2i. And you'll see this root is a conjugate with this root, always will be. And then we get this third root, which is a real root. Let's pause that for a moment, let that sink in. So let's do it. Let's write this in cis form. Okay, so which quadrant? Fourth. What angle? What angle would that be? Pi over 3. Right, negative pi over 3. What would the modulus be? Yeah, double the short leg, right? So 16. So in cis form, this would be 16 cis negative pi over 3. I'm going to add 2 pi k forever, but I'm going to call it 6 pi k over 2, or over 3, sorry. And then what I'm going to do is to find z, I'm going to take the fourth root of said thing. Okay. Fourth root would turn 16 into what? What does that turn 16 into? 2, correct. Negative pi over 3 times 1/4 would be negative pi over 12. 6 pi over 3 times 1/4 would be 6 pi k over 12. I'm not going to reduce that for purposes that at this point should be pretty obvious, but I'm going to keep that common denominator. Okay, so z sub 0 would equal 2 cis what angle? Negative pi over 12. What would z sub 1 be? 2 cis. Yeah, 5 pi over 12. Are we okay, Ethan? So far we're good. Okay. I hope I have an Ethan next year, and I can, yeah. That way all my videos just loop, right? Yeah. What would z sub 2 be? 11 pi over 12, which, Ethan? Is that okay? That's okay. All right. And then z sub 3. 2 cis. Uh-oh. Uh-oh. We're going to run into a problem. That'd be 17 pi over 12, which would be how many from 24 pi over 12? 7, right? So that'd be negative 7 pi over 12. Okay. Now we're going to graph those on what's called an Argand diagram. I'm going to write that out because, yeah. Argand diagram. Argand. Is that I just started it. Thanks, Cole. I'm going to graph these. A radius of 2 cis negative pi over 12. So radius of 2, and then I'm going to rotate negative pi over 12. So that would be the location of z sub 0. Okay. Then z sub 1 will be 5 pi over 12, which is just short of pi over 2 by the same amount. So that'd be z sub 1. There's going to be some symmetry here. You might be thinking, why don't you just sketch this line straight through? Yeah, I think you're probably on the right track there. That'd be z sub 2. I want to see this, though, because it's going to look cool. Okay. And then z sub 3 will be down here. Negative 7 pi over 2 would be right about there. Oh, wow, what happened there? Right. I'm graphing those. Negative 7 pi over 2 was converted, what was it? 17 pi over 12 to that negative pi to pi domain. Oh, over 12, yeah, and then over 12. So what's cool about these is that if I do the 5 roots, well, I did 4 roots, and what is this shape? Square. If I do 5 roots, it'll be a regular pentagon. If I do 6 roots, it'll be a regular hexagon. And if I do an infinite number of roots, what shape? Circle. Yeah, it's pretty cool. Why is that? For the childs, let's do this one. I gotta get a different pen color here. Let's go yellow, yeah. Yellow just for the McDonald's effect. Yes. Oops, plus W. Okay, so some might say, why would you factor out the 4? And you'll see in a moment why. But using quadratic formula, I'd do negative b plus or minus square root b squared minus 4 times a times c. Oh, cool. What happens with the 4 and the 4? They gone. All over 2a. Bam. So what would w equal? Well, it equaled negative 1 plus or minus the square root of negative 16, thank you, over 2, which would be, oh, Halo, hi. W would then equal -1 plus or minus what? What's the square root of 16? Yeah, so 4i, right? So there are two values. Those are our two solutions. Those are our two zeros. So how do we write those as roots? Well, this is how we'd write those as roots. I would take, and I would, let's go with this one to start. -1 plus 4i over 2. If I were to bring that over to the other side and make the whole thing equal 0, what would happen to the 1 and the 4? Yeah, they'd flip signs. Right, so it'd be W, oh shoot, plus 1 minus 4. So that'd be one of my factors. Okay. What would my other factor be? The conjugate of that. Bam, factored. Does that ever cross the x-axis? No. No, that doesn't. That doesn't. All right, I think that should be a good lead enough.